Why does the power rule work? Isn't that a mystery? I mean, it just seems like this magical thing, this absolutely magical thing. For example, if I have a function, x to the fifth, and the derivative is 5x to the fourth, right? We always bring the exponent down and subtract 1. Well, certainly we can understand when we have a nice, polynomial or a nice power function like this, yeah, we know that every time we take the derivative, that we have 1 degree less. So that part makes sense. But why does that cool little trick work? That the exponent becomes the coefficient? Why does that work? Hmm, let's think about this. And I'm going to give you a hint. It has something to do with expanding binomials and with, therefore, Pascal's triangle. By expanding binomials, I mean something like, if you have x plus h squared, and if you expand that, right, that's going to be x plus h times x plus h. So that's going to end up being x squared plus 2xh plus h squared, right? If I have x plus h cubed, that's going to be x cubed plus 3x squared h plus 3xh squared plus h to the third. You remember this pattern that we discovered? Let's do one more. I have x plus h to the fourth. It's going to be x to the fourth plus 4, x to the third h plus 6, x squared h squared plus 4, x h to the third plus h to the fourth. Yeah, if you recall, we discovered a whole bunch of cool patterns. Pause the video and see if you can find the patterns if you're not seeing them. Yeah, one of the patterns is that your exponent of your first term goes down. So it's x squared, x to the 1, x to the 0. X to the third, x squared, x to the 1, x to the 0. X to the 4, x to the 3, x to the 2, x to the 1, x to the 0. And then your second term, h, goes up. H to the 0, h to the 1, h to the 2, h to the 3, h to the 4. But the coefficients, where do those coefficients come from again? They come from Pascal's triangle, or at least that's one place where you can get them. Okay, Pascal's triangle. If you recall, I mean, we call that Pascal's triangle, even though Pascal certainly wasn't the one who developed this or discovered it. I think he probably just published it. It was around for, I think hundreds of years before Pascal came on the scene. But remember with Pascal's triangle, this thing is just rife with cool patterns. But one pattern is, of course, that you can add 1 plus 1 and get 2. 1 plus 2 is 3. 2 plus 1 is 3. 1 plus 3 is 4. 3 plus 3 is 6, and so on. And if you recall, this is one way to get our coefficients. So if I wanted to expand, let's say, x plus h to the fifth, I would go to this row right here, right? This is the 0th row. 1, 2, 3, 4, the fifth row. And then all of those numbers would give me my coefficients. 1 will be my coefficient for my first term. 5 is my coefficient for the second term. 10 is the coefficient for the third term. And on and on and on, right? Okay? So think about how we find derivatives. Yeah, limit definition of the derivative. So for example, if I wanted to find the derivative of x squared, I could set it up as a limit definition of a derivative. I could expand that, combine like terms, and find my derivative. That's how we first learned about derivatives. Same thing here. I could expand x plus h cubed right? So do these. Think about Pascal's triangle. Think about the power rule. Think about what you're doing, and I bet you'll see why the power rule works. All right, did you have success? If you expanded this first one out, you'll see that, of course, those first terms always go away, right? And then if you divide your h out from both terms and now substitute in your 0 for h, you're left with 2x plus 0. 2x. Now, if I did it with the cubic, same thing. Those first two cubes would always, the x cubes would always go away. If you divide out your h from each term, oops, I messed that one up. And now if you plugged in your 0, you'd have 3x squared. That would be 0 because there's an h left. That would be 0 because there's an h left. So do you see now where the power rule kind of shortcut works? We know with the Pascal's triangle that 3 is always, for example, we know from Pascal's triangle that term is always the exponent, right? The first term is being subtracted away. The second term will always have a coefficient of, in this case, 3, your degree, and your exponent will be 1 degree less. So x to the third, the derivative is going to become 3x squared. If your original function were x to the fourth, you'd use this row. Your first term goes away, x to the fourth minus x to the fourth. Your second term is going to be 4x to the third h. That h divides out, and so you're left with 4x to the third. There's the power rule. If your function is x to the fifth, your x to the fifth is going to go away, right? Your second term will have a coefficient of 5, because that's how Pascal's triangle works. And it'll be 5x to the fourth times h, but that h will be divided out, so you'll be left with 5x to the fourth. And there's the power rule. Does that make sense? The power rule lives in the binomial expansion, in the Pascal's triangle. If you don't quite see it yet, just spend a little more time and I think you'll see it. Okay? Cool. I hope that was kind of fun.